So now we know how to deal with infinite limits. We're going to look at something else, limits at infinity. It's a little bit different. It's going to feel really similar, at least in the wording. The names are really similar. Here's the difference, though. An infinite limit, we said, was when the y values go up to positive or negative infinity. A limit at infinity, we're going to be saying the x values now are the ones that are approaching positive or negative infinity. So the y values can do kind of whatever. We're going to have to discover all that stuff. But notice over here, x was approaching a specific x value, some real number, and the y values went either way up to infinity or way down to negative infinity. Now we're going to say what happens on our graph when x goes really far out to positive infinity this way, or when x goes really far out to negative infinity. So what we're doing is we're looking at end behavior of our function. So we're looking at the limit of the function, the limit of what the y values are doing as x is going to positive or negative infinity. We'll notice that if there is a value where that limit does exist, then that means there's a horizontal asymptote at that point. I shouldn't say point, sorry, at that number. So for instance, if the limit as x approaches infinity of some function is equal to 4, what that means is that as x gets really, really big and goes to infinity, the y values get infinitely close to 4. So that's what we know as a horizontal asymptote. It's some horizontal line that our function approaches on the ends of our function. Notice that we're only caring about the end behavior here. So this one we have to build up a little bit. What we're going to look at is two different types of power functions. Power functions are just x's raised to some coefficient, or some exponent, sorry, with a coefficient. So here we're going to say n is a positive number, because what we could really do is say that this is like kx to the negative n. So we want to say n is going to be positive so that we have negative of a positive, meaning the exponent's actually negative. This thing is actually in the denominator here. And don't let the coefficient be 0, or else this is a really boring function because it's just going to be 0. Let's take a look at an example of this. Maybe we can look at a couple of examples, and we'll try and build up what's going to happen here. Let's take a look at what happens when we look at the limit as x goes to infinity of 3 over x to the 4. We can just try and guess what's going to happen. Or what you could do is take a look at the picture of the graph. Or what you could do is plug in some actual real test values. So go ahead and plug in big x values to this. Try and figure out what happens when x goes up to, I don't know, like 10,000 or 1,000,000 or something like that. Or take a look at the graph. I'll wait for a second, see what you've got. All right, what you noticed is that when you put in really, really big values, and if you haven't noticed this yet, just pause the video and go try it, is that we get really, really little x values, which makes sense because what we have here is some number being divided by something that's really, really huge. We're taking something and dividing it into like an infinite number of parts, and we're trying to discover what the size of all those parts is. What we'll notice is that if you divide something into an infinite number of parts, all the parts get infinitely small. They go to 0. We could look at a different example where maybe we switch up some of the things that are going on. Let's say the limit as x approaches negative infinity now. Oh boy, we're getting crazy. Of 7 over x cubed. Now the only difference is that when you put negative infinity in here, or we'll just say any very negative values, cubing them is going to make them even more negative. The magnitude, the size of the number gets bigger, but they're in the negative direction. So now we're taking 7 and dividing it by some huge negative value. This is going to be some tiny negative value, but it's still going to be getting close to 0. So what we can say is that for any power function where you've got some number written over x to any positive exponent, because if it was negative, it would flip up into the numerator. As long as x is going to positive or negative infinity, this thing's going to go to 0. So now, anytime we see a power function like this, we just have to take a look and make sure that x is going to positive or negative infinity, and we don't even have to think about it anymore. We can say this limit's 0. That's our first power function. The next one is if we had our exponents up in the numerator. So if we had something like the limit as x approaches infinity of 3x to the 4. Now what we'll notice is that if you put in really big values, x is going to multiply itself 4 times. They're going to get even bigger, and then you multiply it by 3, it gets even bigger. This thing is going to go up to infinity. Well, what happens if we put a negative sign out here? Now, when you multiply all these positive values by themselves, they get really, really big, and then you multiply it by -3, so it goes to negative infinity. Similarly, we could take a look at what happens as x goes to negative infinity of 7x cubed. And we'll notice that if you put negative infinity into here, this thing is going to go to negative infinity. But if you switch the sign on it, what happens is that the whole thing switches, so it will go to positive infinity. What we can do is build a little chart. Since we're talking about end behavior, maybe I'll erase this line so I can get some more space. Since we're talking about end behavior, what we really need to do is look at the exponent, or the degree, and the coefficient. If the degree is even or odd, that's going to tell us something. And we're going to look at our coefficient, whether it's positive or negative. So again, this is our coefficient. And we can just draw up the end behavior here. Any even degree function, the end behavior looks like this. And an odd degree function looks like this. But if we put a negative sign out front, then we flip it upside down. Now, all we need to do, if we had another example, I'm going to do this one in orange just so I can distinguish. Actually, no, I'll do it in green so I can distinguish between these. If we look at something like the limit as x goes to negative infinity of negative 4x to the 7, we're going to say we've got a negative coefficient, an odd degree, and now we know what the end behavior looks like. So what we need to do is take a look and see which side of the graph are we looking at. X is going to negative infinity. It's going really far in the negative direction. So we're looking at this side of our graph. If we drew like a set of axes on here, this would be what happens when x moves really far to the left now. This is pointing up. So right off the bat, I can say this thing is going up to infinity. So all of these are going to be positive or negative infinity, and we can just use this kind of an end behavior chart or look at the picture of the graph to see what's going on. Make sure that we keep an eye on whether we're looking at the left end behavior or the right end behavior. Sorry, that's a bit messy, but we're really looking at what's going on the left side of the graph this way or on the right side of the graph. So that's how we can deal with these power functions. Polynomial functions are a bit different because these are power functions that are added and subtracted from each other. I'm going to do a kind of cute little, I think, proof that we can use to basically just skip through a bunch of this stuff. So I'll write up a bunch of work here. You'll never have to do it, but just kind of follow along and you'll see what happens. What I'm going to do is I'm going to factor out a common factor, and you're probably looking at this thinking, there is not a common factor here. But since this is my class and I get to do what I want, I get to be God here, I'm going to factor out x cubed as a common factor. What I now have is a limit as x approaches infinity of x cubed times, this first term is easy, it's just going to be 1. And now on all the rest of them, what I'm going to do is just divide by x cubed. That's what I would do if I was factoring out a regular common factor. So this is what we've got. I'm going to take a second and just rewrite this where I simplify all those fractions. So I've got my x cubed out front still, 1. Here I'm going to just kind of cancel out as many x's as I can. So I'm just left with 4 over x. And in this one I've got 6 over x squared. And in this one I've got 1 over x cubed still. Now, since we've got a product of these limits, if you think all the way back to what we were doing at the beginning, when we're in our first video, I guess, we said that the limit of a product is the product of the limits. So I'm going to take these two things and I'm going to multiply two limits. So there's one, and here's the other one. and I'll pretty much just stop here because we'll be able to see something kind of interesting happen. All right, now our first limit, let's just leave it. We'll figure out what's going on there. And in the second one, we've got a bunch of terms that are added and subtracted together. Oh, it looks like I missed a sign here. This is supposed to be positive. I just forgot that plus. Let me change that here as well. All the other ones good? Yeah, I think I'm good then. All right, so the limit as x approaches infinity of 1 is just going to be 1. But now for these ones, what we'll notice is that if we look at these limits individually, just by themselves, if x is going to infinity, then these are those power functions. I'm going to skip back a second and remind us. These are these ones. We're just dividing by x's. So let me go back. We'll notice that since I factored out the one with the biggest exponent, I'm guaranteed that all the other ones are going to have more x's in the denominator in all of these, so that when we simplify them, there's x's left over here. So that means all of these are going to go to just 0. So that means I've got this limit times, so the limit as x approaches infinity of x cubed, times this one, which is just 1. What this means is that for something like this, if we're looking at a polynomial, the biggest term is the only one that matters. So I could have skipped all this and just said, well, this is really the same thing. It's just the limit as x approaches infinity of x cubed by itself. Then we'll say, all right, this has an odd power. It's got a positive coefficient, so it looks like this. We're looking at the right end behavior, so that's this side here, so we're going up to infinity. So I don't have to actually do all this work. We're going to say that anytime we have polynomials, only the biggest exponent term matters. Basically, you can think of it like this. When x gets really, really big, that x cubed term gets so big that subtracting 4x squared doesn't actually do anything. This is a lot easier to see if we had some like really crazy exaggerated case. Like, let's just look at this one. The limit as x goes to infinity of x to the 4 minus 1. When x gets really, really big, that x to the 4 term is going to be huge, right? Subtracting 1 doesn't actually do anything. The analogy I like to make is like walking to the shore of an ocean with an empty cup. And if you dip the cup in the water and pull out some water, you could say technically you lowered the water level of the ocean, but did you actually do anything? No, not really. The ocean is so vast that taking out a cup of water doesn't actually really change anything. Similarly, the biggest term of a polynomial, if x is going to infinity or negative infinity, it gets so big it dominates whatever is happening. And so any sort of like plus 6x here or plus 1 is like going down to the shore of an ocean and trying to take some water out and say, yeah, okay, we changed the water level. You did, but did it really actually do anything? No, not really. So what we can say is that for polynomial functions, here's your general definition of a polynomial. This looks really ugly, but all of these are just coefficients with x's, and we don't know what the exponent is. But only this biggest term matters. So any polynomial, you can just grab the biggest exponent term and go back and evaluate that, try and analyze it like it's just a power function. Take a look at the exponent, take a look at the coefficient, figure out what's going on. For rational functions, the nice thing, this is supposed to be q of x here. The nice thing is that both of these are polynomials. And so if we have this big thing over this big thing, you notice I've got different coefficients and different exponents. But in either case, we can just take a look at the biggest terms of each of those things. And then we just have some little fractional thing to look at. Now, that's kind of hard to discuss theoretically like this, so let's actually do some examples. I've got 3. For all of these, what we can say is that only the biggest exponent terms matter. And what I mean by that is the biggest on the top and the biggest on the bottom. So this limit is really the limit as x goes to infinity of 4x cubed over negative 2x. I can reduce this fraction, and now I've got the limit as x approaches infinity of negative 2x squared. At this point, I'm going to go ahead and start analyzing this like it's a power function, because that's what this is. This is a new limit now. This is a power function. Even coefficient, so the end behaviors are going to be the same on both sides, or even exponent, sorry. Negative coefficient, so it's going to be facing down like this. I'm looking at the right side of this because x is approaching infinity. So we're going to say, hey, the y values are going to be going down. Easy enough. Let's go ahead and look at this. You'll notice this is just the upside down version. So now when we grab our biggest terms, and by biggest I mean ones with the biggest exponent, notice that x is going to negative infinity in this case. We've got negative 2x over 4x cubed. When I reduce this thing, I get a different function at the end. Now I've got negative 1 over 2x squared. Notice I've got exponents and x's left in the bottom. This is one of those power functions that we don't even have to think about. We're dividing by something infinitely big. This is going to go to 0. Since it goes to 0, since this limit exists, what we can say is that there's a horizontal asymptote. At y equals 0 on this thing. If you take a look at the graph, that's what you'll see. There's a horizontal asymptote here. So when you move really far to the left now, the y values will level out at 0. And with this one, we'll do the same thing. Grab our biggest exponent terms, see what happens. This one's going to turn out to be a little bit easier, because when we have 5x squared over 3x squared, that's really just going to give us the limit as x approaches infinity of 5/3. This is a constant. Limits of constants are just themselves. So this is just going to be 5/3. So again, we've got a horizontal asymptote. At y equals 5/3 because this limit exists. This one up here doesn't exist. But we still have this general end behavior that we can talk about. The only thing that we really have to keep in mind is that we have to make sure that we only do this when x is approaching infinity or negative infinity. It's really easy to jump into a habit where we just take a look at these biggest exponent terms and we end up doing it when we're not supposed to. If any of these were when x was approaching just a number like 7 or 2 or negative 3, then what we have to do is go back, plug that value in, and see what happens and analyze it that way. Maybe we get 0 over 0, and so we've got this indeterminate form that says go ahead and do some algebra to simplify things. Maybe we get some other number over 0, like 5 over 0, in which case we know it's an infinite limit. There's a vertical asymptote there. We can take a look at the one-sided limits and figure out what's happening there. Or maybe when we plug in the x value, we just get a real number out of it, half. There we go. We know what the limit is. That was an easy limit. So we have to be careful that we only do this when we're allowed to. The other thing that we have to be worried about is to not get in the habit of just taking the first terms. I could write this like 4x cubed minus 6x squared plus 3 over negative 4 minus 2x. And now what we'd have to do is still grab the biggest terms. So just keep an eye on that. Make sure that you're grabbing the biggest exponent in the numerator and denominator only when you're allowed to. Outside of that, that's how we can do this stuff. So to recap, we've got these general power functions that we can look at, and pretty much that's going to inform everything that we do. We're going to try and see what's going on with end behavior using the charts or the kind of thing that I've got going on here. Or what we can do is notice that if you've got things divided by x's, those are going to go to 0. From there, polynomials, we just use the first term. Rational functions, we just use the first terms of the top and the bottom, and we can analyze things that way. That's everything. Take a look at some problems. Let me know if you've got any questions.